Hello and welcome back to the Coordinates Classroom as we explore celestial mechanics as part of our Exoplanet Detection series. Now, thus far we have gained a deep understanding as to why planetary orbits have to be elliptical. It really follows naturally from basic Newtonian physics. But critically, thus far we have been drawing our orbit in 2 dimensions, like on a piece of paper. And, for the solar system, that seems to work pretty well. The orbits are indeed fairly flat. But when we look out to the stars and other planetary systems, well, of course, those orbits could be arbitrarily aligned. And so today, we're going to be moving from 2 dimensions to 3-dimensional orbits. To go from 2D to 3D, we don't really need any new physics, just to take the results obtained thus far and apply some geometrical transformations to them. Previously, we proved that planets orbit stars on elliptical orbits, as shown here, Kepler's First Law. Now, of course, as an aside, we have assumed a purely 2-body system here. Real systems have multiple masses in them, which would perturb the paths of these orbits very slightly, but this remains a very good approximation, even in a bustling place like the solar system. Now recall that our frame of reference used thus far is such that the star, or the sun, lives at the origin 0, 0. This is because we're free to choose any reference frame we want, and historically, Kepler and others thought of planets as orbiting the star. Of course, from the planet's point of view, stood on the surface of the Earth, it appears as though it is the sun that moves around the Earth on an elliptical orbit, not the other way around. It's really just a matter of perspective. In Cartesian coordinates, the orbit is in the xy plane, with x aligned with the ellipse's major axis. A hypothetical observer lives essentially above this plane at infinite z, and the planet, of course, orbits just as we found before. Now, if we choose a random star in the sky, maybe its planet really does orbit just like this, but of course it could be twisted over in an arbitrary way through a large series of rotational transformations. So that means that we need to rotate our elliptical orbit, here a circle, by hundreds, even thousands of arbitrary rotations until we get to the final configuration that we right now can see that planetary system in. And, doing a very large sequence of mathematical transformations doesn't sound like a lot of fun. Is there a simpler way of accomplishing this? It's here that we can use Leonhard Euler's rotation theorem to help us out. He figured out that no matter what the orientation of a rigid body, which in our case we can think of as being like a solid elliptical ring of material, you can always get to the orientation you want just by using 3 rotational transformations. It turns out there are 2 different ways of doing this. There's the Tate-Bryan angles, which are just 3 different axes, so A, B, C, and the proper Euler angles, which always repeat the first rotation again at the end. So that would be A, B, A. But as you can see, that still leaves a lot of options on the table. Now in celestial mechanics, the historical, conventional, standard choice here is Z, X, Z. And, to some degree this is arbitrary, but there is a logic behind this choice. The first rotation is chosen to be Z because the orbit lives in the xy plane. So doing so keeps the system 2D and thus simpler. So making this choice removes the following options. Now, skipping ahead to the third choice just for the moment, a Z is again used, thus following the proper Euler procedure. The motivation here is that the observer is defined as living down the z-axis, so making this the final rotation gives it a direct physical and intuitive interpretation. So this filters us down to just 2 options. It's either going to be z, x, z, or z, y, z. Between these 2, x is chosen. And one advantage of doing that is that the major axis is now aligned with that axis when the first rotation angle is small. Remembering this series of rotations is very valuable when trying to interpret 3D orbits. So let's imagine the z-axis is now pointing right towards you. Here's my orbit. I personally like to remember this as a twist, a roll around the x-axis here, and then once again a final twist. Kind of hard to do this one, but kind of a twist along this axis here. So we have twist, roll, twist. So we know the series of rotations we want to do, and we have our initial planetary orbit. To rotate the orbit, we are going to use some linear algebra and exploit rotational matrices. So we can write that the final Cartesian elements of the orbit, capital X, Y, and Z components, are related to the initial frame by applying the first Z rotation, that's our twist, followed by the X rotation, that's our roll, and then finally followed by the last Z rotation, another twist. Remember that the matrices are non-commutative, so the order of these rotations really matters. Those rotation matrices can be expanded as follows, where we now just need to choose symbols for the angles by which we are making these rotations. As highlighted, conventional notation is to call the first Z twist little omega, the X roll angle, the inclination angle, I, and the last Z twist a big omega. If you multiply through, you'll end up with the following Cartesian solution for the 3D orbit. Now this equation looks a bit scary, but just remember the following. R here is a function of the true anomaly angle f, and really it is that f term, the true anomaly, that is the only thing which is changing in time. All of the other symbols in here are static. As an aside, I want to acknowledge that one of the most confusing things with the notation here is that we already had a symbol which looks a bit like this little omega, but it's not. It's the curly pi symbol. But fortunately, they are straightforward to relate to one another, where curly pi is the longitude of periapse from before, little omega is called the argument of periapse, and big omega is called the longitude of the ascending node. These rotations are not easy to get your head around. I mean, it's just kind of confusing the first time you see all of these symbols thrown at you. So take your time, go through this slowly, and really try to imagine in your mind's eye or using your fingers what these rotations are really doing to this elliptical orbit. If you find yourself getting confused, I think this simplified picture contains the most important things to remember. We start with an ellipse in the xy plane, we rotate it by zxz, representing little omega, inclination, big omega, and we achieve that mathematically using matrices. We have basically got the 3D orbit now, but another geometrical point to consider here is the reference frame. As I said earlier, it made sense to Kepler to put the Sun at the origin, the center, a heliocentric frame of reference. Now we can use any reference frame we want, but not all frames are equal. Because the planet exerts a gravitational force on the star, then the star must be feeling an acceleration by F equals ma, and so we would call any such frame a non-inertial frame. But we can choose a frame that's non-accelerating by just thinking about the center of mass of the system, a barycentric frame. The center of mass, or barycenter, can be found by just calculating a weighted average of the position vectors, weighted by their masses. What this really means is that this new vector, big R, is not accelerating, and we can see that just by considering the result found from earlier in video 2. We can write the relative positions of bodies 1 and 2 with respect to this barycenter by a simple translation. It's straightforward to show that m1r1 plus m2r2 equals 0, and that means that r1 and r2 are really just opposite mirrors of each other, scaled by their mass ratio. In other words, they always lie on opposite sides of the barycenter. And so the line that connects them must run through the barycenter, meaning we have a picture that looks a little bit like this. Taking the magnitude of these barycentric vectors, we get r1 m1 equals r2 m2, which when combined with r1 plus r2 equals little r, gives the following. You can see now that our big r1 and r2 are just equal to little r, but scaled by a factor which depends on the masses. Now, since little r describes an elliptical orbit, that's Kepler's first law, then capital R1 and R2 are also just following elliptical orbits, but now around the barycenter. Very important point then, that means that the star is not stationary. It is itself in a little orbit wobbling around that barycenter. For completion, we can now take the Cartesian orbital elements from the heliocentric frame and easily express the planet and star elements in the barycentric frame. As a test of your understanding, think about how the elements would look when MP, the mass of the planet here, is much, much less than the mass of the star. Maybe even take it all the way to 0. So using some geometry, we have arrived at our 3D orbit and are now able to describe any arbitrary exoplanet system out there. As a test of your knowledge, try writing down all of the orbital parameters that we have covered in the videos so far. So that's things like orbital period, masses, angles. Make sure you know the symbol, the name of that parameter, and most importantly, what it really means. Now, we're almost ready to finally get to our first exoplanet detection method, radial velocities, but we have one more step first to get there. We have to be able to relate this true anomaly angle f to time and vice versa. So in the next video, we will cover this with Kepler's equation. So thank you so much for watching and see you next time in our Kepler's equation video.